Hello.
Good day, everyone. Hi, let me just introduce myself. My name is András Horváth, and it's 3 o'clock here, 4 p.m. For Greek participants. Can you hear me well?
Yeah, of course.
Okay, that's great. So then let me just start. That's perfect. So the only thing is, which is a minor problem for me, I only have a single screen. So sorry, now I will share my screen and hopefully you can see my slides here. But please note that I will not see you during this. So please, it's not an interruption. If at any point you have any questions, want to add any comments or anything, just please say something and I will stop. Okay? Because otherwise I will be unable to see you there. And so with this, I think we can start. The plan is that for uh, 2 hours, in the next 2 hours, I will mostly speak about machine learning and especially aspects of data in machine learning and the role of data or a data-centric point of view in machine learning. And I plan to have like a small break around like at the middle of the lecture, so for 4 p.m. So let's start. So basically, just what everyone knows and what you all know, machine learning and deep learning. You have heard a lot about it everywhere. There are many advantages and breakthroughs in various areas, and even tasks which were almost seemed almost impossible earlier, as like having a proper chatbot, beating human players in Go, or having self-driving cars on the street, are now possible. Some of them is already done and some of them are like close and developed a lot, but so to uh, run this one we need a lot of data, but if we have a lot of data then we can have more accurate solutions than any traditional approach which is available out there. Uh, so yeah, and but training these networks requires a huge amount of data. This gives generalization power to the networks. If you try to train any modern machine learning approach on 5 data points or 7 data points, then you don't really have good results. Because of this, data really matters. So just imagine like what are the samples and what we want to do. The simplest approach is classification. You have the class of green dots or green circles and the class which are represented by red circles, and we want to separate them. And the typical problem which we always face in case of practical problems is that how many data points do we need? How many samples do we need to represent our problem well? And until the solution doesn't exist, we don't even know what the problem is. These are mostly like research questions or development projects where we don't know what like a good solution would be. So it's impossible to tell what kind of variances, what kind of corner cases are in the data. Because of this, our approach is usually a statistical approach to gather as many data points as possible. And with this, we will hope that it's enough to cover all the variances and all the aspects that we have in data. So if we want to do classification with 1 or 2 data points, it's really simple, but we can also think that in reality, maybe the manifold of red dots and the manifold of green dots looks something like this, where you can train an even more proper decision boundary than just between in these 2 points. If our data is not enough, then of course we will have misclassification, and naturally it becomes even worse if we go to the practical application. Maybe after training, it could happen that in real life our points represent somehow like this, that instead of just this red manifold, we also have elements there. And of course, on the training set, our result will be fairly good, and we can classify red and green circles here. But if you go further and further for the training data, our approach will be worse and worse. And for example, here in this region, we don't know where this decision boundary would be exactly, and also that's the same in this area. So it's difficult to tell us. And naturally, what we could do is to gather as many data as we can. And in theory and in the lab, this is a good approach and it works. But in practice, unfortunately, this cannot always be done. So this is what I want to focus on today, that what can we do if we don't have enough data available? So if we don't have enough data, what is our first try? What do you think? What can we do?
We need to come up with some data, right?
We can come up with some data. That would be my second guess. There's even something which is simpler. So if you have some data, but not enough, like a few samples, what would be your first approach? The second for me would be, and it's a really good guess, to gather some more data and gather data. Yes. So I think which comes like naturally is to try an even simpler model with less parameters, because I also see that it's a common mistake sometimes that, trust me, deep neural networks are great. I love them. I use them every day, but they are also a bit overhyped. There are some problems, and the problems might be that simple that even a fairly simple solution can solve this. Traditional methods, a simple equation or something. Even if you use a neural network, you maybe doesn't have to use like a transformer network with 22 layers, but a simple network containing just a few neurons can solve your problem. So if you don't want to just get more data and you think you have a few data points, it might be enough, but it seems that your methods are not working. The first approach would be to try something with less parameters. And here I have to mention something which is a complex and ubiquitous problem in machine learning. And this is called the bias variance problem. So if we don't have enough data, we try something with less parameters. And there's an inherent relation between the method complexity that we try to solve. So in deep learning and machine learning, typically the complexity of the neural network, which means how many parameters we have in our neural network, and the complexity of the data and the problem simultaneously, which means that how complex is our problem and how many data points we have which represent that problem. Because what will happen here, if we have enough data points, and in this example, the number of data points is not changing, and we use a too simple model with a too low number of parameters, and let's just assume that in this case, it's just a simple line, like a first order polynomial, y equals a times x plus b, we will fit this there, and you can say that, oh, of course, but in this manifold, I can see this curve, which is not represented well by this line. I chose a model which is too simple for this data. If I use extremely complex data, well, extremely complex model where I have a high number of parameters, then I will have overfitting where on the train set, I see that everything works perfectly. This fit is perfect. It goes through all the points, but it can also learn something which is not important for the task. For example, if this is true that we are interested in this curvature, then these small like variances in the data can be considered noise. And this model has learned the noise as well, which is not good. And we should be able to find a good balance between the two of them, where we have a proper bias variance optimal point in this one, where we learn from the data what information is in the data, but we will not learn the noise. So overfitting, for example, could happen if you train on images and you want to classify cats and dogs, and your network will not learn the features of cats and dogs, but for example, will learn images based on features which are in the background. A network can learn that, oh yeah, if there is like a red coffee mug in the background, then this is a dog, because in the training set, this is true for all cases. And then this is not a good approach. Okay, and so once we are past this, then we can go to the next step and we can collect and annotate more data. So this would be the next approach. And you have to trust me that in every machine learning project, the most tedious and the most cumbersome part of a machine learning project is data collection and especially data annotation. And even resource-wise, annotating the data takes the most time, and also this also usually requires the most resources in a project. So you really have to be careful when you consider what kind of annotation do you need and how many data points you want to annotate. And for that, it's uttermost important to select the right tool for annotation. There are many good tools out there. Here I mostly just show some examples for images, but just on the next slide I will show some other ones. And you can just imagine that some of these provide like suggestions. Here in this annotator, if you just click on show suggestion, then it will just automatically draw some bounding boxes and will try to automatically detect some of the objects there. And those are something which you don't have to draw. And so, for example, you can think about this, if it's not entirely perfect, it's not good for your project, but detects like 50% of the object, it means that annotation will be just twice as fast. You require like 50 amount of time to annotate your whole data set, or in the same time, you can annotate twice as many objects in this one. And you have also some other approaches where you can do even segmentation, like Encode applies a model which is called segment anything, which is a fairly good and generic algorithm. And with just a few clicks, you can do segmentation. Segmentation is a task where every pixel which belongs to an object should be detected. And you can think about it, how complex and difficult it would be to draw an outline of every object here. So if you want to gather more data, annotation is uttermost important. But let's just consider that annotation is solved, and you have a good team who can provide you the annotation. But the other question is, what kind of data would you like to collect? Because collecting data is fairly complex. And sorry, I mentioned that I will just show you some examples. And this is not like, not an advertisement for this products. For some of them, there's like a fee for using it. Most of them are open source and can be used freely. But these are the most popular ones. You can also find new ones, and you have to know that this area is developing rapidly. So it might happen then in 4 and 3 months, there will be even better and newer annotation tools out there. But these are the ones I'm aware of now, like for images and videos. Encode, Label Studio, Prodigy, CVET is an open source, really good annotation tool. Super Annotate or Label Image. For text, Brett and LightTag. And for audio, Audacity, if you would at any point require to annotate data, then that's good. And so once annotation is solved, and we think that luckily we have all the resources for that one, there's still a problem that what kind of data do we need? And as I mentioned, unfortunately, there are no really good solution for that. Like, what are the corner cases, or what do we want to gather? Because even if we know this, in many cases, we have no control over that. What I mean by this is that just think about that you're like leading a self-driving car company. And it turns out that our cars are not performing well enough in case of snow or fog. Then it's just not enough that, okay, the obvious solution is to get more footage of snowy recordings, because if there's no snow out there and there's not snowing today, then nothing you can do. So usually it means that snowy data is relevant, but you still don't want to draw out sunny data and rain and all the other ones. Because of this, usually you just collect all the data which is available out there, and every new data can help. Some of them are more important, some of them are less important. And so how to gather data? I just want to tell you this, that pre-annotation can help a lot. If you ever want to do a machine learning project in practice, please, if you have enough data available and you start with like an open source data set or something, that's great. But if not, please forget about these traditional usage of machine learning where we do training and we do deployment. Because with this, you can waste a lot of time and a lot of resources. Typically, people consider this that we have a training phase. So we can train a machine learning model if you can provide me like 1 million samples. And that's not a difficult thing, almost like many people can do that now. And then we deploy the model. But in most of the applications, people want to do something new with these models where like this large amount of data is not available. So even in the best cases, people will tell you, yeah, I have like 100 data points or 200 data points. But it's not okay to tell that, okay, that's nothing, I cannot solve the problem with this. Although this is true, what people can say is that we can do active learning. Active learning is an approach, which is a circular approach, where we don't just do training and deployment, but it's continuous evaluation and model training. So what it would mean, and later on I will speak a bit more about this, that if I have some label training data, I can train a new model on that one. And I can use that model on already available data. It's like new data which is coming in and is unlabeled. And from this unlabeled data, I can select the samples. I will show some things later on in this lecture, like what can help you in this one, how to select the samples, for example, without labeling, to tell and to judge like which sample is important from a neural network point of view and which is unimportant. For example, here you can feel that if it's a classification problem and the model classifies your sample correctly, then it's not that useful because it's already good. Those are the really useful samples which are misclassified. But you will not be able to know which samples are misclassified until they are labeled. And this problem should be solved somehow. I would like to later on show you an example for this one. But even if you have a model which is not entirely accurate, pre-annotation can help. So even if you just have a model which is 60% accurate, it means that when these samples has to be labeled, people just have to check them. And they accept 60% of them without doing anything, and that really saves time, which means that only 40% of the data has to be annotated. And then this data can be used again to retrain your model. Maybe now the accuracy becomes 80%, which means that labeling will be even faster, because in most cases, you just have to accept the suggestions of the machine learning model, and iteratively, this development is significantly faster than just doing data acquisition, data labeling, and then training, and then deployment. Okay. So this is one approach, but this is a methodical solution how to get more data and how to get more data faster. But what other approaches are there to just use your data more wisely, or how to train neural network models if not a huge amount of data is available? Another really good and applicable method is called transfer learning. So in case of transfer learning, it was observed that in many complex tasks, as we see like a complex machine learning model, the lowest layers, which are close to the input, they learn really similar features. Because if you think of like a complex machine learning model, it consists of layers. And each layer, as you go from the input to the output, learns something more and more complex phenomenon, since every layer builds on the extracted features of the previous layer. So at the end of the network, like complex things and complex objects are represented, like neurons detecting cars or people or dogs and things like this. But if you go just lower, then at some level, maybe circular objects are detected or corners are detected and things like that. And on the lowest level, just simple horizontal lines, vertical lines, or vertical elements are detected. And since this is a known fact that the lowest layers will know really similar things in everything, and they learn something which are called Gabor filters on the lower levels, then we can just, it's a waste of data to train these kernels and train these elements again and again and again in all applications. Instead of this, what people can do something which is called transfer learning. So transfer learning would mean that if you have a large data set, which is not even seem to be relevant to your problem. And there are really large data sets, for example, ImageNet, where like 1,000 different classes have to be identified, from dogs to cats to cars to everyday object, clothes, and things like this. And the weights extracted from this, so if you train this network on an ImageNet task, can be used directly on a new data set. And then this network will not just start with zero information or just random information at all, but it also does something useful. So what it means is that if I start this model and fine-tune and retrain this model, then I can use my data much more wisely than just training this neural network or any machine learning model from scratch. And so transfer learning is really good and great. And if you think of any practical applications, even if you have enough data, transfer learning can be extremely useful. It's useful because even in the case of a lot of data, convergence will be faster. And so it means that you can train your model in less time and you can train it more efficiently than with just a normal model. So that's again, in a traditional machine learning model, every task is trained separately. If I have a task which is like represented by these yellow dots, then I can train a network system. Once I have to do another task, I will train a newer model for that one. If I want to do transfer learning would mean that I solve this yellow task. That's good. Maybe I have a lot of data points here, and I have some knowledge coming out of this, which is represented by my model. My machine learning model has some knowledge, and I can directly use this knowledge. And by using this knowledge, I mean that I start training my new model from this. This would be my initial model at the beginning. And then by this, training would be more efficient and better. So that's another approach which can help you to increase the efficiency of your data. With this, we will not have more data points. And unfortunately, it's difficult to have more data points, but you can use all the data and the information in the data more efficiently. The next step, how you can enrich your data, is something called data augmentation. Data augmentation is a really cool technique where we can say, and we can approach this from two different ways. One would be that we can imagine that our data set can have different variations. So it means that if an image was taken, for example, of this nice cat, then we can say that, yes, but it's also likely that if, like in another moment, I would have taken the same picture, then this cat would have looked like slightly different. It might be rotated by some angle, might be a bit larger, a bit smaller, might be shifted in the image. So there are some transformations and variations in my data. And I will show you this most with images because those are the easiest and the nicest to be shown. But you can imagine the same thing with all kinds of data, with text, speech, and so on and so on. I try to show some examples for those as well. The other way to approach this problem is that from also a data point of view, there are some different noises and transformations where I expect my model to be invariant to them. By invariant, it means that the model should give the same answer even though I change my data. So if I know that my model should classify this image as a cat, if this cat is shifted in the image anywhere, I still expect my model to say the same thing. If this animal is slightly bigger or smaller, I still expect the model to say the same thing. So I want a model which is invariant to shift, invariant to scale, up to a certain point, of course. If this cat is too small or too large, then maybe I don't want to just recognize it anymore. But I want a model which is invariant to these transformations. And this is data augmentation. So if I have a data point, then I shouldn't just use that data point on its own, but I should use the data point somehow with transformations and possible transformations which are there. So I can just imagine transformations which could have happened during data acquisition. So if I would gather a lot of data and make many, many images of this cat, then they would look something like this, hopefully. And luckily, there are many, many different data augmentation strategies. There are two large libraries which people use for images, for example. One is called ImageAug, the other is called Augmentations. And here you can see some of them. So if you just use an image, which was there, the original. You can't even see it here, but it was fairly close to this one. If you call this library, it will generate you new samples from this data, which contains the same object. Of course, it's parameterizable, like how weird your result will be, how much it can change the color, how much it can rotate it, and things like that. And these are built on different transformations. These transformations can be put into 3 different groups. One are pixel level augmentation, where individual pixels and individual data points are changed. For example, noise is added to that, or the brightness is changed just a little bit. There are contextual augmentations. These are the most complex ones. But for example, you can delete part of the image, because I can say that, okay, if I wouldn't see like the lowest few rows of this image, it would still be the same. So if I delete some features or some region in my data, then still expect the same result. And you can also show it in different styles or in-paint it with neural networks. What would mean is that I cover some parts and I let another neural network fill this out. In the end, I would like to talk about this, or I will talk about this a bit more. And there are also geometry-based augmentations, and these are mostly those which are shown here, where you can make cropping, resizing, flipping, rotating the image, and also any combination of this one. So this is data augmentation in general. In data augmentation, there are 2 different strategies which are used commonly. People first start usually with offline data augmentation. So offline data augmentation would mean that if I have a data set, let's say I have 100 samples, and on each of the samples, I apply 9 different transformations, then altogether I have a data set of 1,000 samples now, because each sample is repeated 9 times. So altogether, that's what I have. And that's great. But what's even better is something which is called online data augmentation. And it means that every time I want to use the sample for training my model, just I apply a random set of transformation when it is used. So in model training, usually you train it in epochs, and you train in multiple epochs, which means you show every sample multiple times. So meanwhile, in offline data augmentation, you create a larger data set, but still show every sample multiple times. In online data augmentation, it means that you basically never show that same sample twice, because every time you apply some random transformation, random amount of rotation, random amount of noise, random amount of color changes. And this means that every sample would be different, which we have like approximately infinite new samples. This is of course not true, because these new samples are not completely uncorrelated with the previous samples. There are a lot of common features with them. So if you do ever do data augmentation, I really recommend you to do online data augmentation. The only problem with this is that it requires slightly more computation, because this is something you have to do this just once, and in every training iteration you have to do these calculations. But still, offline data augmentation performs a bit worse than online data augmentation. Okay, and if these methods could be done, I also want to show you some newer and more recent data augmentation strategies which can be used. And so from this, one of the first is called mix-up, where you can also not just transform single data points with possible transformations, but you can combine multiple data points for composite samples. So what this would mean, and what mix-up does, is that if you have, for example, 2 images, but you can do the same with voice as well, and you want to say that, okay, this is an image and this is a dog, and this is an image of a cat and this is an image of a dog, and if, a cat is represented by the score 1, 0, which means that there's a 1 probability that this is cat and 0 probability that this is dog. On this image, it's vice versa. This is a 1 probability that this is a dog and 0 probability that this is a cat. If I create a composite image where I use an opacity parameter, and this can be different, if the opacity parameter is 0.5, it means that both images are represented with the same weight in the generated new image, and then my label would be 0.5, 0.5. If the opacity for the cat is 0.7, for example, then for the dog image, it should be 0.3, and then the expected label would be 0.7 cat and 0.3 dog. So this is fairly good and commonly used. Also although for the first time it might seem as like a surprising method, but it really works in practice. And by this, it means that, for example, if in a simple setup, if your original data would be just this blue half moon and red half moon here, you can create samples, just randomly selecting 2 samples and mixing them up at one point, which would mean that I will basically get a weighted average of the x and y coordinates. And I can say that, okay, the closer it is to the blue half moon, it's more blue in the class blue, and closer it is to the red half moon, it's closer to be red. And this creates a nice decision boundary between the 2 elements, where the decision boundary even tries to be like at the same distance from the 2 half moons. So this is a data augmentation strategy which really can be used in practice and is fairly efficient. Another approach which I want to tell is really similar to this one. It's called the cut mix data augmentation, where with data points, what you can do is create composite samples similarly, but here the samples are not mixed based on opacity, so just put one on the other one, but based on area. So here you can say that if I have a cat image and a dog image, then the label should be proportional to the 2 areas which are coming from the 2 samples, and the label should be, for example, like in this case, 0.6 and 0.4, and then your network can be trained in that. And of course, some of the relevant features of the cat are covered in this case, but some of the features are still there, and we can expect the output to have like some likelihood that there's a cat on the image because some features are still present. So these are some approaches which can be used in practice and are really great and efficient. Let me just show you another one, which is maybe even better, because I mentioned to you that usually we don't know how many data samples we know, and the reason for this is that we don't know which samples are hard and which samples are easy for our task. And if you gather just 10,000 new samples where our model is already performing well, then it just makes no sense and has no additional information for the training process. Although if you can give me 10,000 samples where my model is misclassifying them and give bad results, then all of these samples are useful because I can train them again. And so there's something called adversarial data augmentation. And this adversarial data augmentation would mean that if we can somehow collect or generate hard samples for our model arbitrarily, which will, like, for example, cause misclassification, then those have a lot of information because it will really represent the feature distances. So, for example, if you want to have a dog classifier and also a muffin classifier, then this is a famous example where blueberry muffins and chihuahuas are really similar to each other, not only to humans, but also to machine learning models and vision models. And so because of this, it's really important that have both samples in your training set if you want to do classification for this one. And this phenomena or this example can be exploited. So there's a really nice paper called like adversarial attacks beyond the image plane, where with a simulated framework, you can optimize samples against your model. So what you can do is that you can have an automatic framework, which are not real images. I will speak a bit more about this. These are synthetic images, but it's really easy to do anything in simulation. So in simulation, you can generate new samples and many new samples. And you can see which are those samples where your model is performing poorly. And by this, you can identify things. For example, if your parameters are not how the car looks like in structure, but for example, what is the size of the car or what is the angle upon I look at this car, then you can modify these parameters and you can have results, for example, where you identify that from the rear view, for example, or the front view, my model is really bad at detecting this one because then maybe from the back, it classifies it as a bus. And then it's obvious that I have to gather samples like this. And I can do this also in simulation, or it also gives me information that in the real life, I should gather some samples from those angles. And if that's possible, that's a great thing, and it can be done in practice as well. Okay. Another even more complex but also usable method is something called self-supervised data augmentation. And Google has especially has a framework called AutoAugment, where you can look at this task as like another optimization method. That here our task would be that I have a limited data set, and what kind of augmentations would be good to maximize the accuracy of the model. And of course, the transformations will depend on what kind of images you have, because if you have street view images or medical images, or you have, I don't know, images, outdoor images or interiors of houses, then maybe different kind of transformations are allowed. But this is because of the image. And Google trained on multiple tasks and multiple data. They trained a complex algorithm of which will try to predict you that if you have an image, what are the useful modifications of this image to add to your training data. So for example, if you want to do data augmentation, you can just call this AutoAugment library, and it will suggest you certain modifications and give you back some modified samples. So this is where AI can be used directly for data augmentation, and it's very generic and great. Another interesting approach in data augmentation is something called the Sinclair augmentation, where we can use some sort of transformation. So for example, from this dog image, I can cut out different parts. And for both of them, I can say that they contain features of dogs. So they should be similar to each other. Here, every time I use the same model and the same network, and I can say that since they contain the same features, their representation should be the same. Again, here, I extract different transformations. Once, like, for example, the whole image, which is grayscale, and this is part of the image with different colors, but they contain the same object, and features like color and size and these things should not be important, so they should be really similar. But all other pairs, like the dog and this chair pair or the other one, they should be as far from each other as possible. And this is really good because we can say that the response between similar objects and similar in the task that they contain the same object should be as close as possible or as similar as possible, and all others should be as different as possible. And this can really improve how your data is used. And even if you don't have enough data, you can still learn features and descriptors which are more generic and can be used well in practice. So just as a last slide about like augmentation strategies and what you can do here, you can do image augmentations, which are geometric transformation, color space transformation, or even do really complex things where you're mixing images or parts of images. In audio augmentation, you can also add different noises. You can add multiplicative or additive noises. You can shift the data. You can change the speed of the spoken words. Whether you can imagine that in a recording, someone could speak a bit slower or could be like speak faster. You can also change the pitch, or you can change just maybe certain frequencies in your data. But these are all possible changes in this one. And also text. In text, you can do augmentations. Also, although text is less noisy, but you can do something like word or even sentence shuffling when a few words are changed in a sentence. This can be done by almost sometimes by arbitrary words, or sometimes this is just limited to some of the words there. Or you can do word replacement and even syntax tree manipulation, where you replace words with their synonyms. This is typically what works in practice. And you can do random word insertion or random word deletion, especially in case of long sentences. If you delete just a single word from the sentence, in most of the cases, of course, not always, but the meaning of the sentence will not change that much, usually just a little. And in case of insertion, usually if you just add more words, more like descriptive words, adjectives and things like that to a sentence, the meaning doesn't change that much. And statistically, like on a larger set, these approaches can work. Okay, so that's about data augmentation, and I just want to show what was your expected output in case of data augmentation. So here you can see two trainings. So this would be just training iteration at step as we just iterate through our model, and this would be accuracy. So if you just train, then the green one would be just a normal training, and the blue is our training with image augmentation. And so if you train it with the green one, of course, training accuracy goes up and goes up quite fast, but test accuracy saturates after a while. The reason that test accuracy saturates because after this point, I sort of do some kind of overfitting. When I learn not the important features in my data, but specific features for those input elements. And that's why I have this gap. And if I use data augmentation, with data augmentation, training increases slower because it means that now I'm presenting a more difficult task there because I have more variances in my data. All the images are rotated, for example, or flipped or changed somehow. It means that it doesn't make the problem easier. It will be just more noisy. So training goes up slower, but also the test curve has a smaller gap than in the normal case, and a significantly smaller gap, which means that part of this gap was caused by these variances, which we added here in training of objects in different scales, angles, and rotations, and we managed to decrease this gap. Of course, this gap will not disappear. That's not really possible, but you can really decrease it. So that's for example, how this training step looks like that. But unfortunately, there's one problem with data augmentation. Usually people say that, okay, that's good because then we will not care about like rotation. And here I just want to show you that's not generally true. Even if you use data augmentation, accuracy-wise, your method will be better. So for example, there's this image of this airplane. And even if this is rotated just a few angles, just 1 degree or so, you can almost not even see this one. Then what happens there is, or maybe, I don't know, maybe this is cropped a little bit, just 1 pixel is cropped. Then the two images look exactly the same, and they are classified exactly the same as like aircrafts. But if you check the representation inside the network, so what is the descriptor, what are the features that this is learned, then on the original input, you get the blue one, and on the transform, you get the red one. And you can see that the two of them, the inner representations, are really different from each other. And so you can have in this one, in a way where you have a mini batch, a batch of original images and some transformed images where just small and minor transformations are just applied on them. And if you do training, you will not just calculate the overall classification in the end of the network, which would mean that I know that these images and these transformations, they are the same, so they should give the same result. But even inside the network, your inside representations can be forced to be similar. So for example, in different layers, you can say that this layer should be scale invariant. And then in this transformation that scale is present, it should be 0. And I can calculate and optimize for this, that it should be as low as possible. And in this case, for example, in this layer, this layer should be even rotation invariant. And I can add this as well. And if you do something like this, that you will end up something even better than earlier, that the representation of the two objects, although there is just a small change in them, are now really close to each other. So in this case, if you force this invariance, then this invariance is learned by the network, but it's not learned naturally. And of course, and if you check this in terms of accuracy, then you get something like this, that the green was the original training, the blue was with normal augmentation, and the red one is with this, where we even force this augmentation on the inside the network. And you can see with this, training accuracy is higher. Okay, that's good because it even helps to learn the invariance faster, and the discrepancy has even decreased slightly, and we have highly better test accuracy, which is the most important thing at the end of training than ever before. So this is a great and good way to use data in training. Okay, another different approach I just want to mention. This is completely different, but related to the terms of data, that if you want to use a data set multiple times, there's a really nice method called data set distillation. Because in some cases, the problem is not that you don't have enough data, but your data set is extremely large. For example, you can think about like there are large image data sets such as ImageNet out there, or simple data sets, but MNIST and CIFAR, which contains 60,000 and 50,000 images. And in data set distillation, you can think about this that like, are there any unnecessary elements in my data set? Are there elements which shouldn't be included because maybe they are completely redundant? Maybe with MNIST, which contains handwritten digits, maybe I contain that exactly or like really similarly looking digit 10 times in my data set. Then I don't need one. And data set distillation is a method for that, how to reduce your data set. You can just remove some elements which are not needed, but if you want, you can even reduce them by combining these images up to like a really low number. So for example, with the samples in MNIST, which were 60,000 samples, it can be reduced to have only 10 samples in the images, but this is just in a research environment, but this can be done. And it's really efficient because after that you can train networks with approximately a similar accuracy, but only just in just I don't know, just significantly less time than normal. So this is something I just wanted to mention. And okay, once we cover the topic of data augmentation, before that I mentioned active learning, and I mentioned that in active learning it would be great if we could select samples which are important for the network and select samples which are not important for us for training. And one method to do this is test time data augmentation, where we will not use data augmentation in training or model, but once our model is trained, what you can do is that if you have data, then the problem is that, okay, we have data can be gathered, but the data is not annotated. We don't know what's on this image. If it would be labeled, that's really good. We can tell whether our classifier is good on that or not. But we want to tell how robust is our model in this data without knowing its label. And this can be done with a method called like test time augmentation. Test time augmentation would mean that in testing, I can have the original sample and check the descriptor on that one, which comes from the model, or even check the class. And I use many, many different augmentation steps where I have new representations. And from these new representations, I can just check how close they are to each other. Because if I end up with something where there is a small variance in these representations, it means that for the network, these samples, although they are augmented, all look similar. It means that there's not too much new information in this sample. If I see a large variance, as in this case in these representations, then it means that the network sees these samples differently, which means that there are some features where this invariance doesn't happen. It's rotated or scaled up or changed in a way where for the network, it looks really, really different than the other ones. And it means that the network is not really robust on this one. So this is a sample which should be labeled and which should be included in the training set. And if the variance is small and the network sees all of them similar, then I can say that it's not an important sample. So together, data augmentation is a good tool to use your data more wisely. And also, it can be used in test time together with active learning, that if you have a lot of data, and usually gathering data is easier because you can just put out a camera, put out a microphone to collect sound and things like that. But to judge from this which samples are important and which samples are unimportant, you can use one approach is to use data augmentation, and you can tell which samples are great. You can select those samples to label. Those will be labeled, and those can go back to the model and do this again and again. And by this, you can train machine learning models significantly faster than just doing the traditional way. Okay. The last part which I want to talk about before the break would be the application of synthetic data. And synthetic data is fairly good, and it's commonly used because if you, and also at adversarial data augmentation, I showed this example where you could just do a simulated environment and generate samples which are difficult for the model. Because if you, because if you generate the data, all the labels are available. This is an example from Intel. The group of Vladlev Kloton in Intel, they generated a data set called Playing for Benchmarks when they use a game engine GTA 5 to generate data for self-driving cars. And there's a huge advantage of simulated data. And this is the fact that there might be certain cases, for example, crashes or dangerous situation, which you don't want to gather in real life. Although you know that it would be useful, people will not just use stuntmen and I don't know, people who cannot drive like deliberately to cause accidents. But in a simulated environment, this could be done risk-free. And in a simulated environment, it's great that the data is already labeled. So for example, on the left side of the screen, I hope you can see the video fairly well. If not, then you can write the paper or check the paper or search for it. Maybe the original video is up in YouTube, where you can see the input, and on the right side, you can see the segmented labels as like something would have drawn that, oh, there's a people, there are people, there's a person, there's another person. And for this, you don't have to do anything. You don't need human work. You just need to execute a script which calculates everything for you. And you can do the same here. Optical flow is calculated, and you can use odometry data, for example, which will give you that if you want to do navigation, that this is the path which your self-driving car should follow, for example. So these are some examples where synthetic data can be used and can be used efficiently. The problem with synthetic data is that, and of course I mentioned the advantages, it's significantly cheaper to generate simulated data, and you can generate cases which would be really dangerous and unwise to do them in real life. But the problems are that simulated samples will never be identical to real samples. Certain noises, minor changes, other things will be there, which is just not how real life samples look like. And unfortunately, machine learning can really exploit this, because if it's a simulated environment, then, for example, the edges at cars will be really smooth, for example, or even if they have some sort of noise, they will have a special noise. And your models can easily learn this one and exploit this. So that's generally problematic. And because of this, we have to do something which is called domain adaptation. Let me just try to show you this one. So let's assume that we have just want to solve the following problem. We are, I don't know, the boss of a self-driving car company, and we want our cars to work in real life, and want them to solve even dangerous situations like this, but we will not have videos of this one. Or maybe we will have just a few. And even if we collect just a few real-life samples, we're a small company and we don't have people who could just label them. So we have just a few and unlabeled cases here. But we can have simulation, and we have a source domain where in the simulator we can generate a lot of footage, a lot of dangerous cases and all of this. And in the source domain, we can also natively generate all the labels that we want. So that's cheap and easy. So the native solution would be that, can I just use my source domain and see how it performs on the target domain? So if you just write a normal classifier, a simple neural network, when we have different cars and maybe we have to identify the different cars in the simulated environment, then we have a neural network, put there all these elements and try to classify them. So that's what we see here. We train the network and we can be happy because we can see that, oh yeah, it solved this task and it works almost perfectly well. That's good. What happens if we try this out on real life data? So if we change nothing, just instead of the simulated images, we will input some real life images, put it on the network, and we will check what sees. We will see that the whole network will perform, I unfortunately miserably, and it will give really bad solutions and will not recognize anything, because the features that are learned are specific features for the simulated domain. So this seems that based on this, simulated data is not the way to be used in practice. So, but you also know that people use simulated data. So what could be the solution? Here, the original problem is this, that unfortunately the features are really specific. And although this is the sketch, I just want to use this to explain the problem. Let's say that in the source domain, somehow I can just show it in 2 dimensions, but these are really high dimensional spaces. One of the classes, like the minus class, has a manifold like this, and they are oriented like this, and the pluses are like this one. And so, unfortunately, if I do classification on this one, then I find some separating boundary which split them well, and that's great. It seems to be okay, and on the source domain work well. But the target domain is slightly different, and also that property is still there, that, for example, the minus class is up and the plus side is down, but I don't know that, and I don't see that in practice. I just trained a simple model on that one, and that simple model will go through here on this one and cause a lot of misclassification. And the target domain is slightly different, and on that, this would be great. So I just want to tell you an example how this problem can be solved. And a simple problem for this is something called style transfer. So since there are simple differences between data sets, so for example, this is a simulated environment, and this is from GTA 5, and there's a real data set called cityscapes in practice, which were recorded in Germany. This is a representation task that how would this image look like if I would record it in Germany? And since in both data sets I have a lot of data, I can create a network, and this is called a style transfer network. In the second half, I will show you how this actually works, that will cause this image and we'll show it in the style of the original data set. So I can just, instead of just having this nice arbitrary features, I can make it more real life and turn it to more real, where you can see many things have changed. So for example, the pine trees in the background, sorry, the palm trees, they look more like palm trees or European trees because this was recorded in Germany. Also, it's like quite interesting that since it was recorded in Germany, it was recorded by a Mercedes, and in all of the images there's a Mercedes logo somewhere in the screen, and also from this image the Mercedes logo was put there. And similarly, if you try to do that the other way around here, this is the real image from Cityscapes, and it can be represented how it would look like in GTA 5. And you can also see that these trees turned into pine trees, and the colors are more bright and things like that. But this transfer is something that can solve this task more or less. So, and with this, I think I reached like the first half of what I wanted to tell you. And please let me know if you have any questions. I see someone typed that whether you could have lectures or not. I'm not sure exactly what you mean by this. You mean the slides? Okay, yeah, the slides can be uploaded, and we were asked that we could share these. And yeah, so what I can do now is I can just share my slides here, but also as far as I know, all the slides would be shared like globally and would be given to everyone. Yes, please. Please, Artur Shakyan,
yes,
if I'm not pronouncing your name right.
Yes, hello, thank you. I wanted to ask about the style transfer you showed. So it's done by generative adversarial networks, right? So I want to know if diffusion models can achieve something similar, like if they can transfer from one style to another.
Yeah. So so this is done by a generative network. I will speak a bit more about in the second half. This network is called Cicada. It's a cycle gun. I will show that one. Diffusion networks are not that great with style transfer, although they are becoming better. They are really good in just generating data from noise, much better than GANs. But with conditional generation, they are still some problems. But like, for example, what people try to do now is conditional text generation. So like one of the recent things that I have seen is EmuEdit. I mean, it's not that recent, it's a couple of months old. And I know it's not the same as you asked, because I haven't seen style transfer. So my answer is that I don't know any diffusion models which are good in style transfer, but this is a similar conditional method, which is amazing. It surprised me, where you can give like text inputs to a diffusion model and it changes the image in more or less that style. But even here, the style is not represented by an image. So it's not two images and style. So it just, like here you can see where it say that make it a watercolor painting. This is a style transfer, but not a style transfer in that sense that it's between two different domains. Where I show like, I want this image in the style of this image. It just, I can describe what the style is, then it works. So my answer is that I don't know. I'm pretty sure that if someone would have a lot of data, they would also be possible to do something like this. But I'm not aware of a good style transfer diffusion model.
Thank you.
Oh, please, thank you. Let me know if you have any other questions. If not, then I will also be here. I just have a drink and just water. I mean, don't worry. Just go out and let's have like a 5-minute long break, and like 4 or 5 we can continue. If you come up with any questions during that, just please paste it here or raise your hand or something, and I'll be back and we can discuss it, and we can continue then in like 4 minutes. Okay, so welcome back, everyone. Then we could just continue after the short break with the second half, and we will exactly continue with what came up, that generative models and some of these elements, but we'll try to cover some aspects of that. And I'm happy that, oh, sorry, I want to just have this as a slideshow. Okay. And I'm happy that you're aware of diffusion models and all these things. Please note that this is just an introductory course. There will be other courses also in this program, and also otherwise where even more advanced models can be learned. But I think it's good to see the basics and historical building blocks which lead us to current diffusion models, which are great in image generation or data generation otherwise. Okay, please note again that I will not see you now. I just only see what is shared on the screen. So if you have any questions at any point, it's really not a problem. I'm happy of this. It's not an interruption. Let me know, make some noise somehow, and then I will try to stop. Okay, so then, yeah, so how was this generated? And we will look into adversarial networks for this generation. So we want to look into different problem types from a data point of view. We typically have classification problems, and detection problems are also similar, where we have a high dimensional input space, and we will decrease it to a fairly low dimension. So as we go in our network layer by layer, the representation will be typically smaller and smaller and smaller, and this condenses information. It will just somehow, from the high dimensional input space, we map it to sometimes even a single bit if it's binary classification. There are also other approaches like image-to-image transformations or data transformations in general, where I start with some data with a given dimension, and the output is similar in dimensions, although the channel number can be different if I represent them by different colors or represent the different object types and different channels. But in theory, what we do here is that the input and the output of the network are really similar to each other. Autoencoders look similarly, segmentation networks look similarly, and there are many, many approaches. All of them, we do some sort of data transformation. But also that's true that inside the network, sometimes typically people decrease the representation to make some nice embedded space where we would think that this here in the middle, where we have the smallest representation, the data should be meaningful somehow. And on the third end, we have data generation as a task. And so to see data now, we can have a smaller dimensional random values, for example, 100 random values. And from these 100 values, we want to create, or a random image. This is just a sample, so this is more than 100 samples. But from 100 random values, we want to create a larger dimensional image according to some distribution. So according to that, it should have some sort of elements on it. And for example, we want to create a network which will generate faces, for example. And the problem here is that if we just want to solve this, and probably all of you know already how to train a neural network for this task, we could do this, that I present a random input. I present this random input to the network does something. I put here an extremely complex and great neural network. It puts out an image, and I will compare this image to a face image here, okay? And for training this network, I need some sort of loss function. What would be a good loss function which I can use here? Well, probably you heard about like cross entropy that's used for classification and things like that. And I don't know what would be your first guess. My first guess in such a task would be like an L2 distance, which is a square distance between pixels. If we want to compare two images, then this seems to be like a good distance metric. The problem is that if you train such a network with L2 distance, you end up with something like this, where you can see that, well, the network is generating faces. It's not that bad. We like even before neural network, this would have been considered awesome and great. But it's not that good, because I can see faces there and it learns some structure, so that's okay. But you can see that all of them are blurry. I hope you can also see them on the shared screen, but it's not just because of sharing of, or I have a low bandwidth or something. The images are blurry, and the problem why these are blurry is that as we train the network, unfortunately, L2 is a really nice mathematical function, like the squared distance, but they are not specific for faces. So what happened is that, okay, there's a face, and maybe this comes out from the noise, but I will compare this with a random face, and the background could be basically arbitrary. And here, the background pixels and the pixels from the face are considered with the same amount. If you also consider like a reference face for this, for example, I select one face for every image, and for this I selected the same, then it will never be exact. And in another approach, I might select that same reference face or the same input noise with another reference. And this causes this blurriness. So just to put it in another way, the problem is that the loss function that I am using is not space specific. Every pixel in the pixels of the eyebrows, the pixels of the nose, or pixels in the background are considered in the loss function the same way. And since they are considered in the same way, I get this diffuse method, because if I, that's one way of minimization. If I just put out always a gray image, that's a minimal level of noise, because it's as far as black in pixels and white pixels, so it's in the middle, but it's not a nice solution, not what I want to have. So that's an inherent problem, that if you use a mathematical function for this one, that's not great. And what would be a good function to compare faces? Well, I don't know any of that. I don't know any mathematical functions which could do this, but we know that neural networks can approximate arbitrary functions. So if there's a function which can distinguish between faces and can tell whether it's a face or not, that would be a fairly good function. So I could just train a neural network, and ideally, let's say I can train them, which can tell me whether what I generated is a perfect face or not. Then I could put it here in the loss function and use this network, since this network is also differentiable. Here, the only requirement what I need from this functionality is that it has to be differentiable to let me train this neural network. And the neural network in itself is differentiable, so I could just apply this. And this will bring us to critics, where instead of a loss function, we will use a critic which will judge how good our solution is. And it turns out in practice that it's not necessary to train this critic first, and then we train this network, but the two networks can be trained simultaneously. So you can think about it, and this is typically the story how GANs are explained, that let's assume that we have a painter who doesn't know anything about the world and is blind, or at least his eyes are covered, and paint paintings randomly, okay, at the beginning. And we also have a really good and smart, nice detective, but he doesn't know anything about paintings at all here. And we can do the same thing, that first, I can just generate some painting with this random painter and get some samples of real paintings, and I can show it to this critic. And this critic knows in this test that I will tell them that these are the real paintings and these are the fake paintings. From this, he can learn what the difference is between the two. Once he learned what the difference is, I can just train my painter based on this one. So now I train this part of the neural network. I train my critic. It can identify that. And if it's identified, then I stop training this one, and I will start training my painter. I will propagate the error back, which means that he will make some paintings, and the real paintings. I ask my critic, okay, how did you decide this? What's the difference? He will tell us that maybe you're just using the color red all the time. That's the difference. And then we will tell this to the random painter, and he will change his behavior and improve a little bit, which means in more mathematical terms that now I just use this as a simple function and propagate the error back to this neural network. And this neural network will train. Once it's trained, it will generate a newer batch, a newer set of random images. And on that, I will train the critic a bit more, and so on iteratively, until both of them are training simultaneously, and both of them are training together. So if you try to see this, with training, you should end up like this. That I have two networks, and maybe, sorry, first I will just describe the geometry here. So this is what a generative adversarial networks looks like. And this can be used for data generation as well. That's why I mention it here. So these two networks, there are two networks here, a generator and a discriminator. This is my critic, the discriminator, and the generator is someone who wants to generate new and new samples. So its task is that the input is some noise and it generates a fake sample, and that's the task. And in one step, what I do is that I get some real samples as well. And first, I don't train the discriminator. The discriminator is just used to classify which sample is fake and which sample is not. And its decision is propagated back, and on it, the generator is trained to generate better samples, which means like more similar samples to the real ones in the feature space of the discriminator. So it doesn't mean necessarily that they have to be the same, but it means that it should fool the discriminator. And so if it can fool the discriminator, then we can switch training and train the discriminator again to identify some sort of difference between the real data and the fake data. And if we do this iterative training long enough, then we will see that both will become better. The discriminator will learn to detect in the end really minor and really subtle differences and tell what are the problems, and the generator will generate better and better samples and better fake images. And in training in loss, you should see something like this, that here at the beginning, you can see that in this region, the discriminator's loss is increasing, which means that the generator is making better and better samples. It can more or less learn how to fool the discriminator. And after that, we will stop training the generator and we'll train the discriminator, where here the generator's loss will increase and the discriminator's loss will decrease. So it means now the discriminator is learning and the generator is still generating the same images, so it cannot really fool the discriminator anymore. And so on and so on. And we do this for a long time periodically. And we will see that eventually the training will convert somewhere where in optimal case, the two loss functions should be both saturated and also at like the same value. And with this, you can generate significantly nicer and better samples and images. So this is like progressive growings of GANs. There are some minor tips and tricks in this, how to create this like layer by layer, which is called progressive growing. And in some of these cases, you can see some artifacts and some blurry regions there. But let me just show you if I can the video from NVIDIA. Yeah, if it doesn't pay like this, then oh sorry, yeah, that's embarrassing. YouTube advertisement. But so if you just check, then hopefully you can see this is an older like 6-year-old results, but this is a Celebi data set with some real some of these are real images, and these are the generated images generated by the network. And they, if you look really closely, you can see some parts and you can see what's there, but this was really the state of the art 6 years ago. And by this approach, you could generate data which is really useful. I mean, even if they are not perfect, but they are synthesized data generated by a neural network and synthesized in a way which can be used for training face recognition software, so can be used to train neural networks for classification and recognition. So that's great. These are normal generative adversarial network, but also the question came up that this is great and it's a great toy. Like all generative models are seem like great toys at the beginning, that, okay, I just input some random noise or push a button and then data will pop up. But if I have no control over the data, that's not really good. So what people try to do is, after this, something is called the conditional GAN or CGAN, where we have our input noise, this was Z, and then these are the fake samples generated, these are the real samples, and we also have a condition here. And the condition is embedded here that, for example, I will tell that, okay, generate me samples with this condition, and the discriminator sees both the generated samples and the conditions. And if the generated sample is not good according to this condition, then the discriminator can really easily spot this out and discriminate based on that one. So the generator will fast learn what conditions are. But let me just show what conditions mean. For example, you can specify the location of the object. These are fairly simple GANs and old results, but just to show you that you can do something where you can put down, like, for example, a rectangle and show that, okay, the object should be here. Like, you should generate a bird randomly. These are just random bird images, but then the bird should be here. And when you show a bird image with this condition, and for this on the real image, you need detection, like a detector will detect the bird. You can easily see if the bird is not the current position. So by this, you can have some effect on the generative network, and you have some effect how the samples are generated. But for example, if you want to generate persons, you can generate that, okay, this is where the head should be. Or with birds, again, you can give exact positions where the beak, the belly, or the legs should be. And then by this, so it means that I give those coordinates to the discriminator along the images, and for every image there's a condition in training. So this could be done. Another great and still commonly used application of GANs are super resolution GANs, so SR GANs, because in super resolution, that's the same thing that if you see a low resolution and blurry image, then it can be really difficult to identify how the original image would look like, because you can have some mathematical constraints, like, for example, typical man-made images have some sort of low entropy. It means that there are sharp edges and things like that. But like how sharp or how different edges are in this region, it's almost impossible to tell. And with super resolution, the problem is that for one low resolution image, there are a high number of possible solutions which are all good. That's the same problem with image generation. If I give you just random noise, there are thousands or millions of possible faces which could be generated from this noise. So there are multiple good solutions which can be done. And if you try to use a nice mathematical function to evaluate these ones, then unfortunately, this mathematical function will be stuck in a local minima, which is not good for one specific element, but in the middle of all these elements, which is in the middle of this manifold, which is like not far from each of them. So traditional methods and traditional loss functions cannot do something where there are multiple solutions to select one. It will give you back the combination of all the possible solutions. But GANs are typically really good with this, that they can select one possible explanation and one possible solution, like how this could look like, and that's why they are also fairly good in super resolution. Another possible application with conditional GANs, for example, is pix-to-pix. You can try it out and just have some games with this. But if you like draw certain objects here, of course, the type of object has to be known, whether they are cats or handbags or shoes. Then from the silhouette and from the edges, you can just generate the data itself. So these are like just conditional GANs inside of this. And a really nice application, and I think this is one of my favorite for conditional GANs, is image colorization. Since this is the same problem as what you have seen earlier, that if you see a black and white image, or maybe it's even better with this fish or with this car, there are multiple good solutions for this. Okay, the sky is blue, we naturally know that one, but this car could be like, okay, it's a sports car, so that maybe limits the possible colors, but could be yellow or green or blue or red or something like that. That's the same for this fish. I mean, if you don't know fish that well, I don't know. So for me, this could be even white or bluish or some other colors. But there's some possible good solutions. And if you train this with a traditional loss function, then you will get just like an average gray color or an average of all the possible good solutions, which is like really ugly and doesn't look well. But GANs are possible to give you back one solution, which is likely. Like here, say that, okay, the sports car is red and this fish is yellow, and these are two possible solutions. So, and as you can see here, that this is still an area where GANs are commonly used at the applies. Networks which can do colorization are mostly built on adversarial neural networks. Another application which is like even still applied today, but diffusion models are now still used here, and they have a bit better performance, but today we will not speak about them, is image painting. So image painting would be where we have the original image, but in training we delete certain parts of that, and the task would be for the network to fill out these parts based on the context around them. And of course, this is really easy to test this one, because I could use just an L2 loss function or something. But if I, like, for example, cover both eyes of this lady, then there are multiple solutions. It's impossible to tell whether she had like blue eyes, green eyes, or brown eyes. And most likely, of course, she had brown eyes because that's the most likely in the human population. But still, it's not possible to tell. And with a mathematical loss function, you get an average solution, which is not nice. With again, you can select one solution which will work, but of course, in certain cases, it's not ideal. Here you can see that for this lady, like this method generated two different eyes, and well, that's far from being optimal there. Okay, so let me just again try to show you this example. So this is the image painting video from NVIDIA, and this model was trained by NVIDIA, and you can see that like here the image is covered, and here the neural network is running online. So if you like more or less like delete an object, then it try to just extrapolate from the surroundings and try to fill it out with certain elements and certain regions. So if there were branches, then it will try to put some new branches there. If you like cover all the road, then of course it will not try to continue that, but just from the surroundings, try to guess what was there. And even that's the same with mountains or objects and other parts. So basically that would be it, and that's how you can see how conditional GANs can be applied in practice. Okay, so going back to the slides, the next thing that I want to speak about is that although GANs, and that's the same with stable diffusion, which and even modern neural networks, like stable diffusion does diffusion in an embedded space, but still, even with them, but especially with GANs, the problem is that the inversion of them is really difficult, and it's a heavily researched problem. It's a problem which still not solved. And by inversion of GANs, what I mean is that so the normal input is that I use random noise, like a low dimensional input. This is usually called as like the embedded space, like a smaller dimensional space where I can determine my inputs, and I check the outputs. Then it's difficult to tell the way back that if I give you an image, what would be the embedded representation of this image? It can be found, but it would be nice if the spaces would be interpolable, or I would have some effect what it does. And by this I mean that conditions are okay, but it would be great that even I could just find out what this data space does, just not by predefined conditions, because if you define conditions first and train on that, that's okay. But maybe I want to change something in this lady, I want to change her hair or something, then it would be great if I would know that if in the input vector I change these elements or that element, then her hair would change. And unfortunately, with the current state of GANs, and also in stable diffusion, it doesn't seem to be likely. So the problem here is that these representations are entangled representations. So, but interpolation between them can be done fairly well. So, for example, if I have three different input sets, and all these images are generated by a neural network, so you get this random input, and it gives you this image, another input, this one and this one, and between these random inputs, you can just draw basically a line and move from one input to another one, just continuously. And this is what you get here. So if you move on this line, we'll see the change of this image, that it's nicely goes from this image to this image. So the steps in the embedded space are fairly proportional to steps in the image space. But this is not typical in GANs. This is a nice example. Usually what happens that for many, many points, it gives something to this, this image, and that suddenly gives similar images to this one. That's why inversion is a serious problem, and it's not an easy task to be solved. And so the main idea would be, and there are some nice approaches for that, where we could change certain aspects. For example, if we have an embedded space, and that, for example, we know that this was the original image, and then this was generated, then we could select how to change the parameters in the input. So these are not conditions, not trained on that, just in the input space, what to change to make like this image more masculine or more feminine, or other variables to make this image look younger or older, or have like more hair or less hair, or smiling or smiling less, and all these parameters, if this could be identified. And unfortunately, this is really difficult. In some experiments and fairly simple experiments, this can be shown, but most GANs have something which are called like entangled representations. So it's not just that, you know, I change one parameter or I change a few parameters and it will change like these aspects. But what typically happens is that I cannot just change them individually. Like even as I change gender, I also change hairline, but it's sometimes even worse. Like if I want to change one parameter, 10 or 20 different aspects of the image will change just simultaneously. And the disentangled representation would mean where different properties of the image and different features would be just in different dimensions of the input, but typically not. This is not the case, and this cannot be done well in practice. So that's just about the disentangled or entangled representations. And then I just want to go back to the example which I showed, the cicada, what kind of GAN is behind that for image generation, and it was a cycle GAN. So let's imagine the typical task which was done also in the original paper, that we want to do, instead of generating data, we want to do now style transfer. We want to change an image to another style. The style could mean anything. It could mean the actual style of the image, paint brushes or different features there, or it could also mean objects there. Sorry. For example, in this example, what we want to do, we want to turn zebras into horses in this one. And we could train a normal GAN. This is not yet a cycle GAN. This would be a normal GAN where I have a network, and this is an image-to-image transformation. I showed you networks like this earlier, which gets an input image and an output image is generated from that. So with this, our expectation is, and the input image is a zebra image, and horse images should be created. And I can have a discriminator because I don't know a good mathematical function which describes like how horse sees an object or how much it looks like as a horse. But I can train a neural network on this one. I can just put real horse images here, and I can train this discriminator to identify whether this is a real horse image or a fake horse image. And if you train this network, that's good. If you have a lot of data and you have a ton of zebra images and a ton of horse images, then you can train this, and you end up with a discriminator which can tell you like how horse like is an image or an object, and you will get a network which generate horse images from zebra images. That's good. But you need a lot of data for this one. A CycleGAN is something that says that, okay, if you can do this generation, then you can do the other generation around. And this is a really nice idea where you can say that if I have this network and I have these two steps, I can just invert this network, and the invert of the network will do another mapping which generates zebras from horses. So if from the original horse image to zebra, this is solved and this is what I need, but I can just have the same network in another structure which will generate zebra images from horse images. And here the really good thing is, because I don't know an image, don't know a mathematical function which would determine what a horse is. I have to use a discriminator here. But if I generate horses from this image and generate them back to zebra, then with all due respect, I can expect that the same image will be generated. Because I use some sort of transformation on this one, and I use the inverse of the transformation, both represented by neural networks, but still a transformation and its inverse would give me back the original data. So in the end, I can calculate any mathematical loss function between these two because I want them to be identical. And of course, in training, they will not be identical because it might happen that this function is not invertible, but in training, the network will try to do so, and this is called the CycleGAN. And by adding this actual loss of invariance on the generating and inverting the generation, I can use my data more wisely in training again, because I'm not just calculate how good this image is, but we'll also calculate how good the inverse of the transformation is, and training is significantly faster. And this is a typical CycleGAN, and CycleGANs are used in that way that I will just try to make this. There's an even more complex network like this, which is like the whole setup of this, and this is called a DiscoGAN. I will not speak about this one, but in case of a DiscoGAN, you get something where you use another discriminator on the zebra images as well, and you can also like generate this back to horses and have all the full pairs in this one. And so if you can train this network, this transfer and the transfer back and using again can be used for many, many things. It can be used, sorry, I just showed a video. It can be used to generate zebra videos from horse videos and horse videos from zebras. Although the stripes are really strange and this is generated frame by frame, so the inverse is not that good. But I think what's really nice in this one, that if you check the grass, that even the grass is less green than in the original image, because it was learned that like zebras are usually just live in environments when in the savannas the grass shouldn't be that green. But you can also use this, for example, for style transfer, and you can use this style transfer really efficiently. So, for example, style transfer would mean that you can turn summer images into winter images and vice versa, because the two transformations are directly learned and trained. Or you can use this from like to generate a Monet style painting from a photo, what you can see here. But once this is learned, you can also do the invert, and you can ask like any photos of original photos or Monet or any impressionist painting basically, and generate a real life or real life like photo from this one. But you can also do this to multiple styles, and from a real life photo you can just imagine how it would look like in the style of Monet, Van Gogh, Cézanne, or a Japanese ukiyo-e painting, for example. So this is one sample. Here you can see some inputs and some real images in different styles of Monet, Van Gogh, Cézanne, and ukiyo-e. So this is something where this training can be done efficiently and can be done in a really nice way by using this extra loss of doing a transformation and inverting the transformation as well. Okay, so the last thing what I want to show you, sorry, I messed up here the title. It's not a CycleGAN, this should be an InfoGAN. An InfoGAN is a special case of conditional GAN, where the conditions are indirect. So you could think about this, that in the normal GAN, I don't have this condition, don't have this I, and don't have this Q here. Sorry. So an infogun is something where I can have a condition. The condition is just a random number, similarly to this Z. But the condition somehow could be embedded in the generated image. With the condition, again, here I showed the extra condition, and it went into the discriminator. Here, it doesn't go there, but with an extra step, I try to get out this information. So here I just generate a simple data point. So, for example, a new image. And the fake image and the real image goes to the discriminator, but also goes through another network, which is part of it is shared with this one, which is a classifier. And this classifier tried to tell what was the information which I encoded in this one. And this should also be calculated. So in Infogun, for example, I can put there like a 1, a 2, or a 3, any number, and then images are generated, and somehow should learn this to identify whether I generated an image with a 1 or a 2 or a 3. The effect of this would be that this generator will generate 3 different kinds of images, 3 different clusters of images, because those are easily classifiable to ensure that this number is in the data somehow. And Infoguns in this sense can be very well used to put some information in the generation and in the data type. So for example, what you can do is that put just numbers there, that put 0, 1, 2, 3, 5, 6, 7, and 8 as like an encoded information here. So this is our condition. And the network will learn that if I show this code, then a specific sample has to be generated. Of course, here the problem is that it's not ensured that for the code 0, a 0 will be generated, and on code 4, for example, a digit 4 will be generated. This is not ensured at all, but a distinct digit will be generated for a distinct code, because then it's really easy for the network to identify this. So it means that with Infoguns, basically, I have a knob and I have a parameter which I can change and I can tune to affect what will be generated there. But meanwhile, at conditional guns, I'm explicitly told that this is what you have look for, and this is what you need to generate. Here, I will not tell this one. The only thing I will tell is that this is something important, and put this feature, this important feature, into the generated sample, but the network can put it in any way it would like. So that's a problematic thing, because it might encode digits in other parts. Maybe it will encode how thick a line is, or it will encode how rotated the sample is, or something like this. But you can just try to reverse engineer it in again, and by this you can just have some effect on the certain generated properties. So for example, if you want to generate faces with different angles and things like that, and you're lucky, then from your training you can have a network such like this. Okay. And so now that we are familiar with adversarial networks and familiar with data generation, and I also mentioned synthetic data, I want to show you the combination of the two things. So we ended up there that we used synthetic data, trained the neural network on that. Unfortunately, it was working well on the simulated data, but failing miserably on the real data. So we can use some generative model to make it better. But you can do something even better, and these are called domain adversarial training and domain adversarial neural networks. So, and here the main idea would be that if you think back, the normal classifier on the data, we had some feature extractors, then we had a classifier, and okay, it tried to identify whether there's a car or not in the image. That was great, but was not working, unfortunately. And here we extend this with another classifier, which is an adversarial classifier. And here, the adversarial classifier is a simple task where it should distinguish whether the input sample came from the real domain or the synthetic domain. This is the only task here. So if you have such a network, Now, first we will train this. And first we will train this on the synthetic data. Remember, the synthetic data is labeled, and we have a lot of labeled synthetic samples. So here we will show images of cars and images of non-cars and train this part. We do nothing with this classifier yet. We will just train this as we would do it. But if we train only this part, then it leads to disaster. It will not work. The synthetic data generation will not work. So once we train this for a little bit, and it seems to be working, we go to step 2. And on step 2, we show samples both from the synthetic domain and from the real domain. And we will not train this part, because we cannot train this part because the real data is not labeled. I don't know what is the label on this image, so I cannot train this part. But I can train this one, because I know which is real and which is synthetic. So I will train this classifier, and I train this classifier in such a way that this purple part here is trained normally. So these layers should focus on that to solve this task. So it will try to be as good as they can. This is a critique, if you think so, or it's a discriminator, which can try to distinguish between the two domains. And here is something called a gradient reversal layer, where we turn everything to the opposite. And it means that we will train this green part in this step in an adversarial manner. So this purple part want to have a good solution. So it want to find features which distinguish between the real and the simulated domain. And this is trained oppositely. So it will try to generate features up to this point on which it's impossible to distinguish between the real and the simulated domain. And so what it means is that it has to generate two different kinds of features. For the purple part, it has to generate features which are the same in the source domain and the simulated domain. And for the blue part, it has to generate features which can help to distinguish for the task, distinguish between cars and non-cars. And if you do this training for a long time, then what you will end up with is that only those features can be extracted by this green part, which are identical in the simulated domain and the real domain. Because if not, then it can be classified, and this classifier will detect that. And if it detects that, it will go back, and the gradient will show that, no, don't provide these features because they are not good. So if you train enough, you will just end up with the same features. And if the same features are detected, if we train a task on the simulated data, distinguishing that will learn on the real data as well. And this is a really nice architecture, and it's a good generic method which can help you to use your simulated data in more or less an optimal manner and in an optimal way to cover gaps or cover elements that you don't have in your real data. But you can simulate accidents, you can simulate burning cars and other parts, and use that data wisely. And even if you just add them as like simulated, they have some effect. But if you do it with like domain adversarial training, where we try to like distinguish between the features and just force the network not to focus on distinguishable features, then we ensure that you really train on features which can be found in both domains. And that's a nice and great idea. So just to keep some space for questions as well, that's all, and I will just finish now. And that these are all the things that I wanted to just briefly tell you and list to you. So please, if at this point you have any questions, just write it in the chat. Let me know, say it, raise your hand. Any solution is good for me. I'm not promising I can answer them, but I will do my best to try to answer it. Yes, please. I think I saw a hand. It might have been just a mistake, but if you're like thinking of raising your hand, then please, if you have any questions, let me know. If not, then it means I covered everything so well that there are no questions. No, I don't think that's the case, but still. Yes, please. Okay, if not, then this was for today. If even you have any questions that you didn't want it to ask in front of the others or didn't have to ask it, but want to ask later, let me just please share my email here. So you can find my email now in the, sorry, no, I messed up my
Thank you for
email.
the lecture.
Oh, please, thank you for listening. So now you can find my email in the chat. If you have any questions now you didn't want to ask, or you have any other things later on, if you have any projects, problems, something, let me know and write me, and if I can help, I will try my best. Okay, so then thank you for being here, and then that was all today, and so hopefully see you at like other courses and as well.